Okay, this is an overview of the presentation of today. I will start an introduction, tell you the difference between a global and local optimization problem and finding a global and local solution. I think most of you will already know this, so I will go through it very fast. Then I will try to explain the multistart algorithm as implemented in AIMMS by visualizing it. So we will have some demo that shows the steps performed by the multistart algorithm. Then I will tell you something about the parallel multistart feature, which was introduced in AIMMS 4.9. And I will also tell you something about other changes regarding multistart that we did in AIMMS 4.9. And finally, I will end with some remark and with references. Okay. So today we focus on nonlinear problems and nonlinear optimization problems with continuous variables only. So I will also make some small remarks once in a while for the special case with integer variables, but we will focus on nonlinear optimization problems with continuous variables. So assume we have a one-dimensional problem like this. So we have an objective function fx and a variable x, and that we want to optimize this. So in this case, we want to minimize it. So, and as most of you will know, this problem has a lot of several local optimal solutions, namely the ones indicated by the blue arrow, and it has one global optimum solution. That's the red one. So we are minimizing here. And strictly spoken, also the global optimum is also a local optimum. So a local solver will, like Connaught or Nitro IPOpt, if they solve this kind of problem, nonlinear problem, then they will find a local solution. We don't know which one, and we also have no guarantee of how good it will be. So they might find a global optimum, but they cannot tell us that they found a global optimum. A global solver like Baron, on the other hand, will try to find a global optimum, and if it will find the global optimum, it will also prove that the global optimum is in fact a global optimum. So it's more like a solver like Cplex or Gurobi. If they solve an MIP, then they will find the global optimum, but they also will prove that it's the global optimum. So Baron does something similar to that. Yeah. So for solving global optimization problems, for solving, let me go back. For solving problems like this, a local solver might not be sufficient, so we need something more clever to get a good or maybe the global optimum. So we might have to do something special. So we might have to use a global solver, or we could use multistart. So what I'm going to tell the presentation will of course talk about multistart. And for the special case of complex nonlinear problems, a local solver will do. So you don't in that case you don't need a global solver, and you don't need to use multistart, because in this case we only have one local solution which the local solver will find, and that's also of course the global solution, the global optimum. Okay. So in AIMMS we have one global nonlinear solver, that's Baron. And it has some drawbacks, namely it can only handle problems up to 10,000 variables and constraints. I put the 10,000, the only between quotes, because finding a global optimum for a nonlinear problem is very difficult. So 10,000 might seem small, but for this kind of problems, the proof that to find a global optimum is in fact very difficult. But in practice, we might have problems that have more than 10,000 variables and constraints. So if we want to solve that kind of nonlinear problem, then we have to do something different. So then we have to use a local solver, possibly in combination with multistart. And another drawback of Baron is that it cannot handle problems with goniometric functions, so like sinus, cosinus. It can also not handle problems with external functions, or if in else constraints, and it can also not handle models with x to the power y, where x and y are both variables. And there are also global nonlinear solvers available outside AIMMS, which have the same drawbacks, or solvers like SCIP, Colomico, and LTO. So if we talk about global solvers, we normally speak about nonlinear solvers. I also want to mention here CPLEX, because traditionally CPLEX could only solve convex quadratic programming problems, but since the latest versions, or 12.5, 12.6, it can also solve non-convex quadratic programming problems, and does something similar to solve them like Baron. So that's somewhat global optimization. And this is controlled by the, so if you're interested in that, then this is controlled by the CPLEX option solution targets. And I'd like to mention that both Baron and CPLEX can also handle nonlinear problems with integer variables, and they can also solve them to global optimality. But again, with restrictions, they cannot handle very large problems. Okay, back to local solvers, because we need them if we want to solve bigger problems. Assume we have this nonlinear problem. So in this case, we have a two-dimensional problem with an x and y variable, and here you see the function value. And we have a lot of local optima, so we are minimizing. And you can already see that this is the global minimum over here, the peak over here. And below you see the heat map. And maybe you might wonder why, if we have a minimum is red, maybe the minimum should have been the blue one. Well, we can change the colors if you would like to, but I prefer the other setting. So the red is where we want to go. So we see a lot of minimum over here also, and I can also show you the 2D chart of this. So then we see the heat map with the contour lines. And this over here, the red one, is the global optimum, and we have a lot of local optima, like here, here, here. So we have at least 12 or 13 local optima, and some of them are probably not even displayed because the contour details are not good enough. So this is the problem that we want to solve, and this is also the problem that I'm going to use to demonstrate the multistart algorithm. So if a local solver, so this is on this next page we have the same heat map, but now without the color, so we only have the contour lines. So over here, if you remember, here's a global optimum, and here are some local optima. So a local solver will use a starting point, or if you don't specify the starting point, it will use the point 0, 0. And then it will start to solve. And I will show you that the starting point is very important for the solver itself. It has a large influence on the behavior of the solver. So we start now with 1, 1. Let me double click on it, then it will start a solve. So it come up in this case, which is a local solver, and it found the local solution over here, displayed by this red dot. So now I can take another starting point, double click, will start another solve, and then it will find this solution. We can also go here, start another solve using this starting point, and now it will find this solution. So you already see that the starting point that is chosen has a big influence on the solution, the local solution that is found by the solver. And if we try to get a starting point, use a starting point close to the other ones, so close like in the neighborhood over here, then we will see that you might see a pattern. Well, this one is a bit unexpected, but you can expect that points close to each other will go to the same, will result in the same local solution. So this one is apparently some kind of exception. But if you go, for instance, here, press on it, another solve, then we have the global optimum. You can do it once again here. Oops, sorry. You can do it here and over here. Well, I can play with this for the rest of the hour, but probably that's not what you want to see. So let me stop with this quickly. So the message from this is that for local solver, the starting point has a big influence on the final local solution that is eventually found by the solver. So in the multistart algorithm, we're going to use that. So we are going to generate random starting points in a somewhat clever way, and we will then start the solver, and the solver will then find some kind of local solution. And because we are using different starting points, it might find different local solutions, and then we take the best one and return that to the user at the end of the algorithm. Okay. To use the multistart algorithm in AIMMS, you have to first install the multistart module. It can be found under Settings, Install System Module, and then you have to select the multistart module. I'm not going to do it now because I already have a multistart module installed, which is a bit special because I modified it for this demo. The multistart module itself is an open algorithm, so you can look into it. For instance, over here, it uses GMP functionality. You could maybe expect that if you were familiar with GMP, but anyway, so you could modify this algorithm if you want to, and then you can change its behavior. So here we have some kind of code that you can see, and over here we have some code for clustering. I will come back to that later. So this module can be modified if you want to, and it's written in the AIMMS language, so using especially GMP functions. So to use the multistart algorithm, in this case I used well, we have to generate the map program first. This is a GMP function. Well, if you don't know what this does, I'm not going to explain it here, but there are other webinars that explain it, or you can find other sources over here, somewhere on our website. But here is the map program that you want to solve, and it's translated into a GMP. That's what it does. And that GMP is passed to the multistart module, and this is the main algorithm of the multistart algorithm. Over here we have two arguments, a 20 and a 10. The 20 means that it will the multistart algorithm will generate 20 random points in every iteration, and out of those 20 it will select 10. The other 10 it will select the 10 best, and it is done through some kind of criteria, and the other 10s are thrown away, and then the 10s that are left over, they are processed in that iteration. So the multistart algorithm might start a solve from it. Over here we also have some of the control parameters for this module are used. So the control parameters can be found here, and they are explained in the language reference. This is the iteration limit, so in this case we only do 3 iterations. The thread limits, well, I will come back to that later, and here initial. You don't want to use initial point because that's easy for the demonstration. So it could be that the user selects a starting point, and that could be used, but in this case we don't do that. Okay, back to this page. So I press now F6 by running the main execution procedure, which will start the multistart algorithm. So we have an iteration limit of 3, 20 points, and 10 of those points are selected. This is just still the progress window for the previous solve, so it's not clean yet. Okay, let's continue. So now it's cleaned. So we're in the first iteration. It generates 20 points at random. You can see them over here. The 20s are blue dots. And now it will select the 10 best of those. And that is based on evaluating the objective function. In this case, we don't have any constraints. So it's only based on objective function value. But if you would have constraints, it would also take into account the violation of the constraints. So the violation, the amount of violations that each of the points, the constraints that are violated by each of the starting points, and they are weighted and compared with the objective function value. So in this case, if you remember, the points over here are quite bad. So they will be thrown away if we now continue. See, these are one of the left over. And now the multistart will take 1 point and will start a solve from it. So it took this point over here, the blue point, and it found this local solution, and now it creates a cluster. That's the red ball over here, and it creates a cluster by just taking those 2 points, and then over here take the the center by taking the medium between those 2 points. And now it will take another point over here, another starting point, and it finds another global optimum, which is a local optimum, sorry, which is denoted by the yellow dot. And again, we have a cluster over here. Another starting point is used and finds a different local solution. So we have a new cluster. And then this local this starting point is used, and that leads to the same local solution as before. And in that case, we increase the size of the cluster. So the cluster we already had, it was created when we used 0.3 as a starting point, and now we have this one, and then we get a weighted the medium, the center of this new of this updated cluster is created by using the average, the weighted average of these points. So you can see that 0.4 is not included in this circle yet, but it might, if the circle increases, then it might be part of it. So we don't immediately add it to the circle, but we are a little bit more conservative with adding points to a cluster. Okay, now we continue. We find this, we use this starting point and find this local solution, which leads to a new cluster. Then here we have another starting point, and this leads to this local solution, which in this case is also the global optimum, but yeah, the algorithm doesn't know that, unfortunately. And then here we have another starting point, which leads to a local solution that we found before, so we update the cluster. And then here we have another cluster. And here again, we are going to update this one, this cluster below. Here we found use a new starting point, which led to the same local solution that we've seen twice before. And now we have finished all the solves. And there are some points that are not used. In this case, only one. This point is not used because this point is already part of a cluster. And in that case, the idea is that the chance that this point, if we would use it, then it will lead to this local solution. The chance that that happens is quite big. At least that's the theory. And therefore we can save time by not starting to solve from it, because every time we solve a problem, it costs time. In this case, it's a very small problem, so in this case, it doesn't matter. But if we can avoid a solve, then that's good, because that way we save time. Okay, now the first iteration is finished. We go on with the second iteration. No, that's a mistake. At the end of the first iteration, we first shrink all the clusters. That has two reasons. First, it keeps the algorithm alive, so at a certain moment it could be that the whole space is divided by circles, and then, yeah, well, you would never start a new solve again. Another reason for this is that sometimes a point can be assigned to the wrong circle, and in this way it might be freed somewhat from that circle, and we could end up by starting a new solve from that point. Okay, now we go to the second iteration. We generate 20 points at random. We drop the 10 worst, and then we continue like before. So we start from this point we start a new solve, and we update this cluster. Over here we have a new local solution. Here we update another cluster, and so on, and so on. So we now have finished all solves, and in this case there are 3 points over here, here, and here that have not been used because they are already part of a circle. And if they are part of a cluster, then they will not initiate a solve. Okay, and then now we have the third iteration. Now first we shrink the clusters again, and now we continue with the third iteration. I think you get the drift. So it generates another 20 points at random, throws away the 10 worst ones, and then starts solving again. And over here we now see what we saw over here, it was combining two clusters, so clusters can overlap. You have two, that's okay, that's not a problem. And this is the final point. So you see some points again that they increase the cluster, but they are not part of the cluster over here. Number 2 and number 6 also over here, and number 3 also. So now all solves are finished. Again, some of the points did not result in a new optimization. Sorry for that. And yeah, and the algorithm is now finished. And in this case, it found a global optimum. So this demonstration shows how the algorithm works. So it's generates starting points, it starts solves, but it also tries to create clusters, and thereby avoiding that points that would lead to an already known local solution are used to solve a problem, because solving problems costs time, and therefore you want to do that as less as possible. Okay, back to the presentation. So there are several parameters that can be used to steer the multistart algorithm. So I showed you before the location where they are. So they are the control parameters. So I will briefly describe them. You can also find them in the language reference. The iteration limit speaks for itself, I guess. We also have the use pre-solver. With that you can choose whether you want to use the multistart algorithm in combination with the pre-solver. Using the pre-solve the AIMMS pre-solve has two benefits, namely it will decrease the size of the problem, and therefore normally the local solver will then be able to solve faster the problems that are for which you have the starting points. And the second reason is that the second benefit of this is that the pre-solver will tighten the variable bounds, and thereby the multistart can select better random starting points. So by using the pre-solver you get better starting points. That's the idea. You can also choose to use an initial point. I discussed that before. Here we have the shrink factor, so that's the factor by which all the classes are shrinked at the end of the iteration, every iteration. So by default, the multistart algorithm returns one solution. It stores only one solution, but you can also specify that you want to have, for instance, the five best solutions. The multistart algorithm should keep them the 5 best solutions. You can also decide to show solver progress. I will come back to that later. And the ones at the bottom are used for parallel multistart, and I will explain them in a minute. Okay. Parallel multistart. This was introduced in AIMMS 4.9. So the idea is that you if you have multiple cores on your machine, that you use them. So that's a way to speed up the multistart algorithm. So the multistart algorithm itself is only meant to, well, it's meant to find a better solution, but of course it will slow down the optimization because you're doing multiple solves instead of one solve with a local solve. But this way, with the parallel multistart, you can speed up the multistart algorithm itself in some cases. We will come back to that later. I will show you later on some results. Okay, the parallel multistart is controlled by this parameter thread limit, and its default value is 0, and that means it will use as much threads as possible. And the amount of threads used is limited by the number of cores in the AIMMS license. So if you have a machine with 4 cores, then it will use 4 threads, at least if the AIMMS license allows it. Because to use parallel multistart, for a certain solver, the solver should also be allowed to do multiple solver sessions. And by default, all solvers in AIMMS, if you buy an AIMMS system, they allow you only to do one solver session. But for instance, in the academic license, you have a limit, I believe, of 8, so that's quite large. So with an academic license, you could already start using parallel multistart if you would like to. Important to know is that It uses one solver. It uses only one solver. So, for instance, CONOPT. So it is not possible to use CONOPT for one solve and in parallel with an IP-app solve. There are no limitations from the AIMMS point of view, but because AIMMS allows to do so, but the Multistart algorithm has not been developed to use multiple solvers in parallel. However, you could modify the Multistart algorithm because it's an open algorithm. You could modify it in such a way that you have 2 or even more, 3 different solves in parallel. It's possible to do so, but not with the current implementation. And I have to mention that not all solvers are suitable, not all non-linear solvers are suitable to do Multistart, but I will come back to that later. And the Multistart algorithm can be deterministic or opportunistic. Deterministic means that if you have multiple runs with the same model, using the same parameter setting in the same solver on the same computer, then it will produce the same results. So multiple runs will produce the same results. Opportunistic, on the other hand, is often faster, but then you have no guarantee you will get the same results. And same results might mean in this case that it might have so you might have different results. So you might have a different objective or different solution or different performance. Okay, now I'm going to demonstrate the parallel multistart in an example. So this is a nonlinear problem elect. It can be found on various websites. It's a COPS model. And initially, I only start the multistart algorithm. I use the multistart algorithm when it's using only one thread. And let's see what happens. So again, I use CONOPT. And over here, you see the progress of the multistart algorithm. Below up, you see the overview of the algorithm itself, and below you see the current solve. That's determined by the show solver progress, which is by default set to 0. It's disabled. If you set it to 1, you will also see the solver progress. And this will take about 1 minute. I can already say that. So in this case, we have 16 points, and 8 out of them will be selected. So it will do at most 8 solves. And for this model, it will actually do all 8 solves. So all there are no points. There are no points from found into a cluster. So the clustering in this case is well, not effective, one could say. So we're almost there. So it took about 64 seconds. So of course we had that I forgot to do, but I forgot to set the seed. So we cannot. So without setting the seed, I cannot restart the algorithm without a different performance. So if you set, for instance, the seed option seeds, by using the seed option, you can ensure that if you run the same procedure, then the same starting points, the same random points will be generated. But I forgot to do so. So I have to close and open the project again to get the same, to ensure that the same points are generated by the multistart algorithm. So once again, so before it took a little bit more than 1 minute, and now we're going to increase the thread limit to 4. Well, let me remove this now, but it's good to know that if you set a seed, then you can rerun the procedure without closing AIMMS first, because by using a seed you get the same performance, the same random points will be created. Okay, my machine has 4 8 cores, so 4 threads should be no limit. Should be possible. Of course, my license is good enough. So now again, we run this Multistart algorithm, and from the task manager, we see already that well, around 50% of the CPU is used, and now it's a little bit less because it's at the end of the iteration. Apparently, less problems are solved. But you see that often it's around 50%. And now it was 12% because it had to finish the last solve. So now we see that with 4 threads, the time is more than 50% less. So that's a nice speed up for this problem. Back to the presentation. Okay, I will show you some results. So from runs we did with parallel multistart algorithm for several problems. So this is the same problem as I shown before, namely elect. In this case, we have 2 iterations. So it's a minimization problem with 600 variables, 200 constraints, and 1200 non-zero elements. So it's not that large, but it's also not very small. And below you see the mode. So we have deterministic mode and optimistic mode, and below there you see the number of threads. So 1, 2, 4, and 8, and 1, 2, 4, and 8. So the column for the 1 thread should be similar. They should have the similar performance because the algorithm is in fact the same. But the other times might differ because of the time sometimes differs. So that's not always the same. So you see that in this case we have 2 iterations and we have 8 sample points. So that means that in a maximum of 2 times 8 is 16 solves will be done by the multistart algorithm, and in this case that is indeed the case. So in this case the clustering didn't do much because every point generates a solve, and as expected we see 16 different solutions. And we see the objective is everywhere the same, and the speed up by using 4 threads instead of 1 is about 2.5, and there's not much difference between deterministic mode and optimistic mode. And you see also that for 8 threads the speed up from 4 to 8 is not that large. From 1 to 2 is okay, from 2 to 4 is also nice, but from 4 to 8 it's limited. So this is one example. This is another example, train-F, which is a bigger model, about 60,000 non-zeros. We did this time we choose 5 iterations with 8 sample points, so at most 40 solves. But in this case, we see that the amount of actual solve performed is much less. It's less than 10. It's between 6 and 8. And even though all the solves were led apparently to the same solution. So in this case, in this example, you see that the clustering has an effect. But we also see that in this case, the speed up by using more threads is limited, and there's a good reason for that. Namely, the first problem that is solved, so the first point that is used, takes much longer than the other solve. So the first solve takes 60 seconds, and in fact, for these experiments, CONOPS was used, but in fact, for the first solve cannot converge to an infeasible solution, so it didn't find a feasible solution. The other solves were solved. The other problems were solved in around 10 seconds. So that the first solve, the large solving time of the first solve, has a large impact on the results, as could be expected. So here we see for the first 1 thread we have the first one takes 60 seconds and the rest take about 10. So then we have about 110 seconds and some 5 seconds for the algorithm itself. So that makes sense. And over here, yeah. So 60 seconds for the first solve, you cannot expect that, and the algorithm itself will yeah, you can expect that it will take something like 60, 70 seconds or so. Okay, another example. This is a very small example, and also very easy to solve. In this case, we use a lot of iterations and a lot of sample points, and again, only a fraction of them result in actual solves. But yeah, it's a small problem. Every problem is solved very fast, and in that case, you cannot expect the speed up. So if you have a problem that is solved very fast, then using multistart has no benefit. The speed up is very limited. Although by accident, there's more accident. It's not by design or because the method we are maximizing here. So if you use multiple threads, then it finds a better solution than with one thread. But that's just an accident. Okay, and the final result is for this model called Plotter, which is a quite large model with more than 100,000 non-zeros. In this case, we use 3 iterations and 32 sample points, and now you see that the time used is very large because it's a quite difficult problem. So 3 times 32 at most 96 solves could be started, but we see that about 20% of those points do not start a solve. And in this case, we see that the speed up for opportunistic is almost 3, with 4 threads, and with 2 threads is 1.85, which is very nice. It's a very nice speed up. With the deterministic approach, the speed up is much less, so it's only 1.88 for 4 threads. So this example shows that especially the opportunistic multistart mode is very efficient for this model. And if I would have chosen only 8 sample points, then the objective return would have been less. So in this case, using the sample points, the amount of sample points was somewhat needed because we are maximizing and the objective value is worse than if we use 32 sample points. So these examples show that in some cases multistart can be very useful, especially if you have non-trivial models. But for non-trivial models, you could always, for small models, you could also use a global solver. Okay. Which solvers are suitable for parallel multistart? Well, the solver, to be suitable for parallel multistart, the solver has to be thread safe. So it should be able to, that the solver can be called, solver DLL can be called from multiple threads. And in AIMMS, the card and nitro are thread safe. Not thread safe are minus as a not, and Baron is also not thread safe, but yeah, using a global solver in a parallel multistart algorithm does not make any sense. Then you can better use the global solver directly, of course. And there's a special case, that's IPOpt. And its thread safety depends on the linear solver that is used by IPOpt. So IPOpt uses a linear solver to solve sparse, symmetric, indefinite linear systems, and does that several times. So the algorithm that IPOpt uses requires it to use that kind of linear systems, and they use a linear solver for that. And there are several possibilities which IPOpt can use. So IPOpt can use MUMS, which is not thread safe. Can also use MKL Paradiso, which is thread safe, or ASL, which is a library of functions, and that's also thread safe. Unfortunately, only the non-thread safe one, MUMS, is available currently in AIMMS. You can, however, use these, but then you have to do something yourself. Namely, you have to get these libraries or build those libraries yourself, and then you have to build the IPOpt linked also yourself, because that IPOpt link then has to use these solvers. It's doable, and instructions can be found on Coinora, on the AIMMS links project in Coinora. So it might be interesting to also offer MKL Paradiso, because then of course you could use IPOpt, which is a free solver. You could solve it used in parallel multistart, and also MKL Paradiso has also some performance benefits over MUMS. Same for ASL, but ASL is a commercial package. So we could consider adding support from MKL Paradiso AIMMS, and if you think that would be interesting for you, then please let us know. You can send an email to me or to our support email box, and to indicate whether you think it's interesting that we link IPOpt to MKL Paradiso. It would be interesting for information for us to know. Okay. Besides the parallel multistart, we also changed, we had some other minor changes in AIMMS 4.9, so now AIMMS, the multistart algorithm also uses the pre-solver by default, but previously it could also use the pre-solve, but it was disabled by default, but now it's switched on. We improved the documentation language reference, and also the progress window is improved. So on the right here you see the progress window of the old multistart algorithm. So this is the progress displayed while the algorithm, the multistart algorithm is running. So you basically see only the progress information of the current solve. In the new, well, like we've seen before, the new algorithm, you see actually the more information about the multistart algorithm itself. So you see the iteration, the number of solves, the number of solutions found, the best solution at the time. And like shown before, you can also combine it. You can also show the solver progress of the current solve that is controlled by this parameter show solver progress. And if you have multiple solver sessions running, so if you use parallel multistart, then it will only show you the progress information of one of those solves, namely the first one. Some final remarks. Well, not unimportant, Nitro has its own parallel multistart algorithm. It doesn't do any clustering. It basically generates n random points and then does n solves. The benefit of it is that you don't need any extra license requirements, so you have to buy Nitro, but you don't need any additional solver sessions, like which you would need if you would want to use the AIMMS parallel multistart algorithm with Nitro. So that's this option is cheaper, at least if you want to buy Nitro, if you want to use Nitro. And another remark is that the GMP AWA algorithm, which is also an open algorithm, which is used for extension on the programming. I will just briefly remark this, so you don't have to remember that. But if you are interested in this, you can later on look it up in this presentation, which we will make available on our website. And it can so the AOA algorithm can be used in combination with multistart, namely inside the procedure solve NLP problem, which is used by this algorithm. You then have to replace some code, namely the code over here, which executes one NLP solve, and then you have to replace it by a multistart solve, which is done over here. So in that way, if you have a nasty non-convex problem, you might end up with a better solution, because in every iteration you solve, you might have a better NLP solution. That's the idea. And that's almost the end of this presentation. We have some references. Well, the language reference, as I already remarked, contains a chapter on multistart algorithm, namely chapter 70.2, the AIMMS 4 documentation. And here is a paper that was used as a motivation for this, for building the AIMMS multistart algorithm. So we didn't use exactly what's written over here, but it has been a motivator for our multistart algorithm. And I'd like to finish with the announcement of the next webinar, which will be called Optimization Under Uncertainty Using AIMMS, and will be presented by my colleague Ovidio Listus. This webinar will take place on Wednesday, November 18, and again at the same time frame as now. And you can register by clicking on this link.